Hello and welcome to Lecture 2 for Building Materials and Testing for UG1 Civil Engineering at the University of Kurdistan. I'm Mr. Alan Collins, and today I'm going to be taking you through the first of our materials, aggregates. So in this lecture we're going to be learning what are aggregates, what are the different properties of different kinds of aggregates, what they can be used for, some of the applications within civil engineering. Then we're going to look at how we can test some of these properties for different aggregates. So the question we need to ask ourselves first is, what is an aggregate? The word aggregate comes from Latin, which basically means a whole formed by combining several separate elements. So the council was an aggregate of 3 regional assemblies, would be a way of describing it in a government setting, but more often than not in English we talk about aggregates in terms of particles of rock or soil or clay, a material or structure formed from a mass of fragments or particles loosely compacted together. So it usually is referring to crushed rock or soil products, and in civil engineering we use these for foundation, road construction, drainage material, concrete manufacture where we mix it with cement, or for fill where there's a hole that we need to fill in before we can build on it. We would use an aggregate. So these are some pictures of some very typical aggregates. I think you need to remember that aggregate is not just rocks. You can see the aggregate in the middle there. That's a crushed rock, clearly. But you look at the one on the left, that's actually sand. Now what's the difference between the sand and the rock there? The only difference is the size of the particles. It's actually the same kind of material, it's the same mineral composition. The only difference is the size of the particles. Now if you look at the one on the far right, you can see that, maybe not that clearly, but the one on the far right, there's different size particles which have a larger range. There's some very big particles and some very small particles, and they're all mixed together. That's what we would call well graded, and we'll get to that in due time. But for what you need to know now is the one in the middle is what we would call open graded or uniformly graded, which means all of the aggregate particles are roughly the same shape and roughly the same size, whereas the one on the right, there's a bigger range of sizes, and we call that well graded. So how do we manufacture aggregates? Well, you've probably seen this around if you've ever driven around Kurdistan. There's these areas called quarries where they're breaking rock out of a mountainside. I don't know the term in Kurdish, but the term for these places in Arabic is mahajar. It's a place where they make rock from larger rock, and then they basically crush it. This is a very cool rock crusher. You can see in the top right of that picture, a digger is placing large rock boulders into the machine, and that's crushing it into a much smaller particle size, making aggregate. And you can change the settings on these machines to make different size aggregates. And once you can change the settings and get different size aggregates, you basically can get various piles of different size rocks ready for the buyer, the civil engineer, to come along and collect whatever size aggregate he needs. So I'm sure you've seen sites like this around. There's quite a large one, by the way, in Iran, if you've never been to one. Now, the properties of aggregate, they are They can be influenced by the shape of the rock, by the how well graded it is, the size of the rock. But first off, I want to talk about the properties of the individual particle, namely, what is the aggregate particle made of, what kind of rock, and what sort of properties do they have? Well, there are three kinds of rocks, and I'm not going to go into any detail on this other than very surface level, b'shekl suti, that an igneous rock is basically a rock that has either come from a volcano or it has cooled lava. So it was lava underground and it's cooled. That's an igneous rock. A sedimentary rock is an igneous rock or metamorphic rock that has basically been eroded, which means it's been broken down and moved to a new place before it's compacted and made into a new kind of rock. Now, a metamorphic rock is basically a sedimentary rock which has buried itself deep underground, and I'm meaning kilometers underground, where it's been placed under really high pressure and it changes its crystal structure. So if you look down here at the bottom, you can see a few different kinds of rock. Limestone and sandstone are examples of sedimentary rock, and you have lots of that here in Kurdistan, a lot. Granite is a type of metamorphic rock, and then finally marble is also a kind of metamorphic rock. Now what's interesting is look at the difference between marble and limestone, just in the way it looks. They look completely different. Well, actually they are exactly the same chemical mineral. Marble is basically limestone which is buried deep underground, and then it's been pressured and squeezed and put under all sorts of pressure, and the molecular structure, the matrix, changes and it turns into a much denser, more dense and more strong rock called marble. And of course marble is a very common material here in Kurdistan. It's used a lot for posh things, so fancy kitchen bench tops or gravestones in the cemetery. Often they will be made out of marble. Now, you'll notice on this slide as well, there is a number of percentages given with those different kinds of rocks. First off, in civil engineering, nearly all applications of aggregate mean that the aggregate needs to be hard and it needs to be durable. That means that it can't break down from the wind, from the rain, or from ice, and it can't erode. The reason for that is anything we build in civil engineering has to last many years. Civil engineering projects are very expensive. The smallest civil engineering projects I was ever involved in were about $50,000. So, and the largest one was about $120 million. That was my civil engineering career. So the very poorest, smallest of engineering projects is still a lot of money. And you can imagine one day if you're building a house, I don't think even in Kurdistan you can build your house, your villa, for much less than $50,000 US. Now, because it's expensive, it has to last a long time. Now, if it's not hard and durable, it will weather and erode. Basically, as soon as it starts raining, the rock will turn to sand and it will break down. You don't want that. So a property we're always looking for for an aggregate in civil engineering is that it needs to be durable. It needs to be stable. It can't be broken down by weathering and erosion. Now, what determines whether it's durable and it can withstand this weathering and erosion? Well, one of the most common physical properties that actually influences whether it will weather and erode is something called porosity. Now, porosity is how many pores there are in proportion to the total volume of rock. So what is a pore? Now, a pore is basically a small chemical link inside the chemical structure of the molecule inside the rock that water can react with and connect with. So if you think about this, if you have a chemical which has an ionic bond inside it, that ionic bond will have positive and negative charges around it. Now, water will stick to anything that has a positive or negative charge, because water, it's in the shape of Mickey Mouse, a water molecule. It's two hydrogen atoms stuck to an oxygen atom. And I can talk more about this in the tutorial and show this to you on the board. But basically, one side of a water molecule is positively charged and another side is negatively charged. So when it comes into contact with any chemical charge, it will stick to it, and that's called a pore. Now, basically, this means that if you were going to take, say, a rock that weighed 1 kilogram and it was bone dry, and then you soaked it in water, and then you let it dry, so the surface of it was dry, there would still be water stuck inside the rock particle. And these are water molecules which are sticking to the pores, these charges inside the chemicals. And that means the rock will be heavier than it was before. So let's say you weigh it a second time after it was soaked and then dried, and it's now 1 kilo 100 grams. We would say that has a porosity of 10%, because it has the ability to hold 10% of its mass inside the rock by pores. 10% of its mass in water inside the rock. So you can see here different rocks have different porosity. Limestone has, depending on the limestone, the porosity can be as high as 5 to 20%. Granite, 0 to 2%. Sandstone, again a big range, 2 to 20%. And marble has very little porosity. It's normally no more than 0.3%. Now, if you have a rock with very high porosity, that means it will be prone to weathering and eroding. That means that this limestone rock on the left, if that has a porosity of say 20%, if that is left out in the rain and then it dries and then it rains again and it dries, gradually that's going to break down and turn into dust. You do not want that. And I mean, it will take many years, but then civil engineering projects, any civil engineering infrastructure has got to last many years. We saw in the last lecture a Roman aqueduct which was over 2,000 years old. And one of the joys of civil engineering, I think, is that many of the infrastructure that you will be building in your career will last your lifetime. You're going to be able to point to it to your grandchildren and say, see that, I built that. And it's really enjoyable. It's a joy that electrical engineers or software engineers just don't enjoy. But porosity. It's the volume of water that can be held inside a rock particle by chemical reaction, by bonding with electrical charges. If this is unclear, ask me more about this in the tutorial. But here's an example of porosity. Now clay, you can see that picture on the left. What's happened there? You can see it's all cracked. Well, you know what that is because you've seen this down by the river. When it was wet, it was soft and muddy, and then when it dried, it cracked. But what made it crack? Well, basically, there was water that soaked into the clay and it formed bonds with chemical charges, positive and negative charges, throughout the material. And when that water evaporated, it broke down. Those chemical bonds were broken, and so it disintegrated. And that's why clay particles are generally very, very small. And I mean smaller than normally 10 microns in diameter. It's because of the high porosity. Now just think about that. Would you want to build a house out of clay? Well, not if it's not stabilized by cement or anything, because the moment it rained, your walls and your roof, they will turn to mud and you'll be sitting in a mud puddle. You don't want that. The reason that that is not stable and durable is high porosity. Now, remember what I said. Porosity is all about water being able to connect chemically and form chemical bonds with positive and negative charges inside the mineral itself. Look at this rock on the right. It's called pumice. So pumice is a rock which is volcanic, and you can see it's got lots of holes in it. It's sometimes called the Swiss cheese rock because it's just got all these holes in it. And because of all these holes and air voids inside it, it actually floats. There's a very famous river in New Zealand where there's a lot of pumice, and there's just thousands of these rocks floating down the river. It's quite amazing. See if you can find an example of pumice in the geology lab when we're back at the university. It's a very interesting rock. Some of you may have pumice in the home. Occasionally women like to have a pumice rock inside the shower for scrubbing themselves, so maybe you've seen one in your household in the bathroom. Now, a lot of people, usually non-engineers, people I like to call muggles, they think pumice is porous because to a non-engineer, porosity is about water being able to pass through an object. That is not what porosity is. Porosity is where water will chemically bond with a positive or negative charge inside the rock. So clay is porous. Pumice is not porous. The property of water being able to pass through an object is what we would call permeability. And it means it's a very good material for drainage. But that's not what porosity is. Porosity, chemical bonds with positive and negative charges inside the rock particle, inside the mineral. Now, high porosity means it's not very durable. It will break down. That means it's not very suitable for nearly all properties of engineering, for nearly all applications, but it's also not very suitable for concrete, because what concrete is basically aggregate particles stuck together with cement. What happens if those aggregate particles turn to dust? You're basically going to have a very weak concrete, and so it's not really suitable for concrete. And that's why you always have to make sure your aggregate, if you're using it for concrete, is clean, meaning it doesn't have any clay or soil or organic material inside it, because that makes the concrete very weak. So this is an example of a concrete where the aggregate used to make the concrete, it was rather dirty. There was a lot of mud inside the aggregate, and they mixed it anyway with water and cement and made the concrete. And look at that concrete. A year later, it's full of all of these tiny cracks throughout the concrete. What's caused that is the aggregate breaking down, and then it's causing lots of little cracks throughout the concrete. It's not a good sight, so that's why you need to have clean aggregate. Sometimes it's called blue stone because aggregate often has that blue colour. For concrete, you want clean aggregates without any dust or soil or clay or silt inside it. So remember, the lower the porosity, the higher the density. This is a general rule. There are some examples here where that's just not the case. An example would be pumice. Pumice has very low porosity but also very low density. But high density means that water can't really get inside the material as well. There aren't so many channels it can go into the rock by, and that means there's less contact and there's therefore less opportunity for it to react with positive and negative charges. So generally, the more dense a material is, the more dense an aggregate is, the more durable it is, and you can see that in the bottom point. That's a general rule. So if you can't measure porosity, you can always measure the density, and that can give you some good indication on how durable it is. But the other thing that influences how porous a material is, and therefore how durable it is the type of minerals inside the rock. Now some minerals are far more reactive with H2O than others. So carbonates react with water very easily. You basically get carbon dioxide and CHs. They react all the time. Sulfides and iron oxides are they react a lot less. But the aluminates and silicates, if you can get a rock with lots of aluminates and silicates, you're going to have a lot less reaction with H2O. So as you move from left to right there, you will have less porosity, and therefore you will have more durability. Now normally, as an engineer, you're not going to be able to measure the chemical composition of a rock regionally. You can't test it for how much carbonates there are or how many aluminates there are in the rock. You're just going to test it for porosity, but this is background knowledge for you to know what causes some things to have higher porosity than others. That's why limestone has a range of porosity from about 2% to 20%. It may be, some limestone might be more dense than other limestone. Some limestone might have more carbonate in it than other limestone. And all of this influences how porous the limestone is and how durable it is. So how do we measure density? Well, this is a very simple equation here. Density is mass over volume, and typically in engineering the unit we will use, especially for aggregates, is kilograms per meter cubed. So this is quite a famous formula. It's called Archimedes' principle. So Archimedes was a very famous philosopher and mathematician in ancient Greece, and he was given a crown to him by the king of the ancient Greeks, and the king said, "I have a suspicion that this crown I have, which is made of gold, is not actually gold. I think I've been tricked. Archimedes, I think the person who sold me this crown conned me. I don't think it's real gold. Can you test this gold to make sure that it's real?" Now, the way you would test gold normally in the ancient world is to test the density. Gold is a very dense metal, and so you would weigh it and then compare it to the volume to find the density. Now, the issue is with if the gold came in the shape of a cube, that's easy to find the weight. You can weigh it on a scale, and it's easy to find the volume. You just measure height times width times length. But with a crown, it's a very unusual shape. How do you find the volume of a crown? And remember, we had all those exercises in engineering skills about finding the volumes of unusual shapes. But Archimedes couldn't figure out how to find the volume. And then eventually he had an idea. He was having a bath. His servant poured him a bath, and he got in the bath, and as he sunk into the water, the bath overflowed. The water was displaced and it overflowed the bathtub. At that moment, Archimedes famously jumped out of the bath, and he ran through the streets of Athens naked, yelling, "Eureka, Eureka," which means, "I've got it, I've got it." What he had realized was that if you get a body or any odd shape and you put it in water, the amount of water it displaces, the volume of water it displaces, is equal to the volume of the object. And that's how we're going to find the volume of rocks. Rocks are very unusual shapes, but if we put them in water, it will displace the water, and we will be able to know what is the volume of the rock. And then we can weigh it, get the mass, and from that we can get the density. Now, there's something called specific gravity, which is a ratio. And this is the ratio of the rocks or the aggregates density with the density of water. Now, the density of water is 1,000 kilograms per meter cubed. It's always 1,000 kilograms per meter cubed, or 1 kilogram per liter. But look, here's an example. If you have a granite rock and that has a density of 2,650 kilograms per meter cubed, you would divide 1,000 by that, the density of water, and that means the specific gravity is 2.65. Now, this is just how we generally describe density as specific gravity. Now, what's the unit of specific gravity? Well, obviously there's no unit because it's a ratio. You're dividing a density, which has a unit of kilograms per meter cubed, against a density, which has a unit of kilograms per meter cubed. It's unitless. But what you're saying here is that for the density of water, this granite particle is 2.65 times as dense as that water. So here's some typical specific gravities. So these are different kinds of rock. So dolomite is a type of rock that is, if I remember correctly, I maybe have this wrong, but it's basically compressed ash. It's a type of volcanic rock, and that's got a specific gravity of 2.8 to 2.9. So that would mean that the density is about 2,800 kilograms or 2,900 kilograms per meter cubed. Now, another example would be sandstone. Sandstone, the density is 2.5 to 2.7 specific gravity. So the density is 2,500 or to 2,700 kilograms per meter cubed. Look at coal. Now, coal is a very undense, or it has very little density. If you have a charcoal from the barbecue, it does feel quite light. It's 1.3, so it's still a bit more dense than water, but it's not very dense for a rock. On the other hand, basalt, which is basically cooled lava, it's a volcanic rock. You don't have a lot of that here in Kurdistan, very common in New Zealand and Iceland and places where there's volcanoes. But yeah, the specific gravity can be as high as 3 times the density of water. Specific gravity of 3. It can be that high. Now, all of this is a general rule of thumb. Remember what I said. Generally, the higher the density, the more durable an aggregate is. Another rule of thumb is generally the higher the density, the better the compressive strength of the rock. So we don't use coal for building foundations. It's very weak. And you've probably held coal in your hand before, and it doesn't take a lot. You can crush it in your hand quite easily. So you wouldn't want to be building things out of that in civil engineering. But materials like granite and andesite and basalt, they've got good specific gravity, and they generally have very good compressive strength, which makes them suitable for a lot of applications in civil engineering. Okay, so now let's talk about moisture content. When you buy an aggregate from the quarry, you're never going to have a bone dry aggregate. There will always be some moisture, there will always be some water, and that's going to affect the mass of the aggregate. It's going to affect properties of the aggregate. Now, this moisture can be in 2 places. It could be on the surface of the aggregate, where it's just sort of sitting on the surface of the particle, so it's got a wet surface, or it could be inside the aggregate particle, connected to the crystal structure and connected to mineral molecules by positive and negative charges, and that is pore moisture. Remember what we said about moisture content with porosity. So we've got 3 different examples of an aggregate particle on the bottom there. The bottom left-hand particle, that is oven dry. That is an aggregate particle that was put in the oven. So you see the oven in the top right corner, that was heated to 200 degrees for several hours. There is no moisture in that whatsoever. Now let's say we take that and we put it in a bucket of water and we let it soak overnight, and then we take it out and it's wet and there's water all over the surface. But as well as that, there's also water inside the aggregate particle with the pores, porosity. And that's shown with the example in the bottom right hand corner. That is a wet aggregate particle. Now, if we take that wet aggregate particle and we leave it in the sunshine to dry until the surface is completely dry, that's what we call a saturated particle, meaning there's no water molecules on the surface, but all of the aggregate particles, all of the pores are still charged with water, meaning all of the pores inside the aggregate particle are still holding water molecules. We can leave it to dry for a bit longer, and some of them will dry off and it would be air dry, but in order to get it completely bone dry, we need to put it in an oven again. So with all 4 of those aggregate particles, they will have different moisture contents. Now, moisture content is basically the weight of the moisture or the weight of the water over the oven dry weight of the particle, and then you multiply it by 100 to give you a percentage. So that's moisture content. Now, how do we measure porosity? Well, porosity, what we've got to do is we've got to make sure that we don't have any surface water influencing our porosity measure. So what we need to do is we need to get the top right corner of it being saturated. That's where all of the pores are holding water, but there's no water on the surface. So to do that, we would soak the particle in water overnight in a bucket of water, then we would take it out, put it in the sun, and we would weigh it only after the surface is dry. And that would mean that we have a saturated surface dry weight. Now we would take away from that the oven dry weight and then divide by the oven dry weight, and that will give us a moisture content that we call the absorption capacity. The absorption capacity is the moisture content when only the pores are holding moisture and not the surface dry, not the surface. So if you remember correctly, with that slide I showed you with the different particles, and I said they have different kinds of rocks and they have different porosity, and limestone had a porosity of 2 to 20%, and I think marble was 0.3%. Those percentages were the absorption capacity. Absorption capacity is a measure of porosity. And of course, if we want to get the amount of water on the surface of a particle, we just take the moisture content of the original aggregate and we take away its absorption capacity, and we know how much water is on the surface. So with moisture content, remember, generally the smaller the particle size, that will mean there is more surface area overall. If you have a big truck or 2 big trucks, and one of them is carrying big boulders and then the other one is carrying sand, the sand is, and both fill the trucks, both of them are 6 cubic meters. The sand one is going to have more surface area because there's more particles. That will mean there will be more surface moisture. Now, if a fine particle aggregate, something like sand or silt, has a very high surface area, then if that gets wet, that can actually increase the overall mass and volume of the aggregate. This is called bulking. Now you need to take this into account if you are ever buying a sand or a clay or a silt, because often you will buy it by volume, by the cubic meter or by the ton, and if it's wet, half of it could be water and you're going to be ripped off. This is actually something that I have seen some quarry managers do here in Kurdistan. When they are selling sand, they will sell wet sand because basically it bulks up the sand, and they will fill up the truck with far less sand and they will sell it to you for the same price. So it's something to be aware of when buying an aggregate when it's a very fine particle. It doesn't really matter for larger aggregate particles because the surface area isn't that much. And it also needs to be considered when you're mixing the aggregate in with concrete. So concrete is a mixture of water, aggregate and cement. Now if that aggregate already, and it's a very careful recipe, concrete, it's like baking a cake. If that aggregate already has water in it, that's going to influence your concrete design mix. So it's very important to take account of that when making concrete. Now, if an aggregate has a very high absorption capacity, or it has a very high surface area, so it can hold a lot of moisture on the surface, it's really good for cleanups and spills. So this, you may notice this if you go to certain, it's regulation in New Zealand and the developed world, maybe not so here in Kurdistan, but if you ever get to go to Europe or another country from the developed world where they have slightly higher environmental standards than Kurdistan, I'm not attacking Kurdistan here, it's just a reality. If you go to a petrol station, there will always be a big bucket of sand at the petrol station. Now the reason for that is if you spill petrol, you have to clean it up. And the way you clean it up is you throw sand on the ground, and that sand will soak up the petrol. And then once it's soaked it up, then you shovel up the sand and you can throw it in the bin. That's a way of taking care of environmental spills. You can also do the same thing with sewage or vomit. I noticed once that we had a student who vomited in class at UKH, and Lemma, who is the Nepali cleaner, he came down and he threw sand over the vomit, and that was to basically soak up the vomit, and then he could basically clean it up with a brush and a dustpan. So that's one of the uses of an aggregate with a very high surface area or absorption capacity, or both. It can be used for cleaning up spills. Also, if it has a very high absorption capacity, so something like a clay particle aggregate, that's really good for making a waterproof barrier. Now basically water can't travel through the aggregate because as it's moving through it will bind with the pores, and so water does not pass through it. That's why if you go to an area with clay soil, when it rains it usually floods, it doesn't infiltrate into the ground. So think of certain areas in Kurdistan where it's always flooding. If you go there, I'm sure if you look at the ground you will see that it's all clay, meaning that when the water comes in the flood it won't infiltrate into the ground. The clay forms a barrier that holds it up. So that means clay is really good for making a core for a dam. It's also really good for layers, the layer around a landfill. So landfills are a mixture of waste which is solid but also liquid, and that liquid is leachate, and if that leaves the landfill and infiltrates into the ground it can pollute water supplies, it can pollute wells. So this is a big issue actually in Kurdistan, where people get sick from drinking tap water. The reason for that is because sewage and leachate is going into the ground and polluting the wells. Now, if you were putting your landfill or your sewage into a landfill which has a good clay barrier surrounding it, then the leachate, the liquid, won't be able to get through and escape. If that's not clear to you, I can show you on the whiteboard when we have our tutorial. So let's now talk about bulk density. We've already talked about density, and with Archimedes, density is the density of an aggregate measured in bulk. So before we were talking about the specific gravity of particles within an aggregate, and we talked about how often an aggregate will have a specific gravity of anywhere between 2.5 to 3. But when it's in bulk, you are measuring the density of the entire volume that the aggregate fills up. So look in the bottom right hand corner. We have a bucket, and inside the bucket you've got aggregate particles in the form of the red pebbles, and they all have a density of, say, I don't know, 2.5 specific gravity, 2,500 kilograms per meter cubed. But the issue is look how they're arranged. There's all of these voids inside the aggregate because they don't fit all closely together like bricks or Lego. There's all these voids in between. That means when we take the overall volume of the bucket and we then weigh it, the density, the bulk density, is going to be far less. So a typical aggregate we would be measuring the bulk density. Now the bulk density is going to influence the strength of the material. If it's got a lot of voids in it, like this one in the bottom right hand corner, that air is not giving it any strength. So if it's not very dense in bulk, it will be low strength. So a typical high bulk density will be around 2,000 to 2,500 kilograms per meter cubed, and that sort of aggregate we can use for foundations for buildings and for concretes as well, because that has high strength. A typical density would be maybe 1,600 kilograms per meter cubed. And so we can use this for foundations for roads, and sub-bases for roads, these sorts of things, because it doesn't need that much strength, because it needs to really uphold a truck driving over it, as opposed to the weight of an entire building. And also concretes too, that require less strength. Now a lightweight bulk density would be anywhere as low as 1,000 kilograms per meter cubed. Now that, at that point, usually it has more air voids than it has particles, and that means it's usually very good for drainage. It's very good because it means water can run right through it. It will infiltrate into the ground. So you'll notice with all of those densities, they are less than the densities of the particle on their own. And the reason for that is because the voids have no density, and they bring the overall bulk density down. Now, as well as that, as well as the voids, things such as the specific gravity of the density of the original particle, the size of the particles, the grading, we'll get to that later, that's the range of sizes, and even the particle shape, all of these influence the bulk density. If the particle shape is really flaky, it's sort of a flat cornflake shape, then that's going to have a very low bulk density because it creates a lot of voids. Now, with bulk density, remember the bulk volume is made up of two things. It's the volume of the aggregate particles and the volume of the voids. And so the more void content you have, more void volume, that's going to lower the strength of the aggregate. And so how do we find this? Well, we can use this formula here. The percentage of the aggregate which is made up of voids is the specific gravity multiplied by density. This is for the aggregate particle in its own, so the density of the particle minus the bulk density divided by the density of water, so 1,000 kilograms per meter cubed, multiplied by 100. That gives you the percentage void content, how much of the aggregate is made up of air. Now, when it has a very high void content, it's great for drainage, similar to those very low bulk densities we talked about before. Now, if it has the particle size, the shape, the grading, all of these influence the void content, the void ratio. Now, when you're making concrete, remember concrete is a mixture of aggregate and cement. Now, if the aggregate has a very high void content, that means there's going to be a lot of air particles, air voids, which need to be filled with binder, cement. Now, what's the most expensive part of concrete? It's the cement. And it doesn't actually add to the quality of concrete, it doesn't increase the strength. And so this is something you need to consider with concrete. You need to use a very low void content when making concrete. Now finally, crushed rock normally has a lower void ratio than river gravel. Crushed rock, the rocks are really angular, they're really jagged. River gravel, the rocks and the aggregate particles are really smooth and round. Now, when they're smooth and round, that means that they sort of sit on top of one another rather than locking into one another and corners going into gaps and things. And so that can actually create a higher void content, river gravel. So that's one reason why really high strength concretes here in Kurdistan, they will use a crushed rock rather than river gravel. And I'll show you pictures of these later on too. If that's not clear to you, ask me about this in the tutorial. Oh, finally, in the bottom right hand corner we've got that pumice rock again. Now remember, with pumice rocks, they have all these air voids even inside the particles. The void contents for pumice can often be as high as 90%. And I think we'll leave it there for now. We will begin this another lecture later on, but for now this will be our lecture. If you've got any questions, contact me, and we'll talk again soon. Thank you so much. Bye.
In this video, we are going to take a look at the Los Angeles test, which is a measure of an aggregate's strength, or more precisely, its resistance to fragmentation. The principle of the test is quite simple. A 5 kg sample of 10 to 14 mm sized aggregate is placed in a rotating drum along with the 11 steel balls. The drum is then set to rotate for 500 revolutions, after which the degree of degradation is measured by using a 1.6 mm sieve. The more material that passes through the sieve, the less resistant the aggregate is to fragmentation. Now let's take a look at the test in more detail, starting with sample preparation. The sample sent for testing must contain at least 15 kg in the 10 to 14mm size range. Only material passing a 14 and retained on a 10mm sieve is used. In addition to this, either 60 to 70% of this material must pass a 12.5mm sieve or 30 to 40% must pass an 11.2mm sieve. The sample must be reduced to create two size fractions by using just one of the intermediate sieves. The two size fractions are then washed thoroughly to remove dust, after which they are placed in an oven set to 110 degrees Celsius and dried to constant mass. When cool, the two fractions are mixed together and then riffled down to create a test sample with a mass of 5,000 plus or minus 5 grams. After the balls and aggregate have been loaded into the drum, the front cover is replaced and secured. The power is turned on. The operative then leaves the room, making sure that nobody else is inside. Locks the door. Removes the interlocking key. Places the key into the control box and starts the test. Nobody can now gain entry to the room without removing the key and unlocking the door. If the key is removed, the drum would stop. Inside the drum is a metal shelf that lifts the aggregate and balls, which in turn causes the aggregate to become fragmented. Each ball must have a diameter of between 45 and 49 millimeters and a mass of between 400 and 445 grams. The test is noisy, therefore anyone directly outside of the room must wear ear protection. The test requires the drum to rotate at a speed of between 31 and 33 revolutions per minute. Therefore, it takes about 15 minutes for the drum to complete the 500 revolutions. On completion, the key is removed from the control box. The door is unlocked. And the operative re-enters the room. The power is turned off. The front cover of the drum is then unbolted and removed. The contents of the drum is then carefully discharged into the tray beneath. All aggregate from inside the drum must be removed. The fragmented material is then taken from the tray and washed over a 1.6mm sieve. It's a good idea to protect the 1.6 by using a coarser guard sieve. This sieving operation is done in several stages to avoid overloading. The retained aggregate is then dried to constant mass, allowed to cool, then weighed. Using this equation, we can work out the Los Angeles coefficient, where m is the mass of the material retained on the 1.6. So in our case, the equation becomes 5,000 minus 4216 divided by 50, which gives a value of 16, as we round to the nearest whole number. The lower the number, the more resistant the aggregate is to fragmentation. For more information on this test, please refer to the standard BSEN 1097 Part 2.